So in this chapter, we're going to be studying kind of a new topic, and the topic is discrete probability distributions. So we are only going to be focusing on the first two sections. As I mentioned in the last video, we're only focusing on the first two sections. And I have an extra credit some extra credit assignments available, which involve Chapter 3. So, Chapter 3 is about probability, just basic probability. You know, if you roll a die, what's the likelihood or what's the probability that you'll get an even number? What's the probability that you'll get an odd number? And a lot of students are very familiar with that topic. So I decided to turn it into an extra credit assignment. Feel free to go ahead and do that. That might help you if you are not that familiar with probabilities. Okay, so for this section, we are focused on 4.2, and we're going to learn about binomial distributions. Okay, so we have 1, 2, 3, 4, 5 objectives, but when you look at it realistically, we don't have that many objectives. So how to determine whether a probability experiment is a binomial experiment, this is key. Number 2, how to find binomial probabilities. We're not going to learn using the binomial probability formula, which involves n choose k and factorials. We're not going to do that. So in fact, we can cross this out. Using technology, yes. Formulas, no. Binomial table, no. Again, there will not be tables provided on the exam, so please make sure that you are learning how to use technology. So let me go ahead and highlight that. I have videos. I have a video that is posted in the link for TI-84 resources. And as I'm working these examples, I'm going to be using a TI-84, and I'm going to be calling out the commands for using a TI-84. So really make sure that you practice using technology, because that's the way to do it nowadays. Okay, and we will construct and graph binomial distributions, and lastly, we will learn formulas for finding the mean, variance, and standard deviation of binomial probability distributions. So if you recall, there were these long drawn-out formulas for finding the mean and the standard deviation and complicated keystrokes on the TI-84. When your distribution is binomial, the formulas are simplified. So we won't get into proving these formulas, but we will get a chance to practice the applications and understand what the formulas mean for our particular circumstances. Okay, so let's go ahead and look at how to tell if an experiment is a binomial experiment. Now, you've got 4 different requirements. The first requirement is the experiment needs to consist of different trials, okay? And the same trial is repeated a fixed number of times. So maybe you are structuring maybe you're structuring a clinical trial, and the trial is to give a patient a pill and see if the blood pressure of the patient drops below some magic number, right? Now, if you perform this trial on 200 people, that means that you have 200 trials. Okay, and what we would use for that is we would say in this example, we would say n equals 200, right? So your experiment is repeated for a fixed number of trials, where each trial is independent of the other trials. What this means is that what happens to one trial doesn't impact what happens in the other trial. So for the example that we're talking about with this blood pressure treatment, Typically that's going to be independent trials, because if I give a pill to one patient, that's not going to impact whether another patient's blood pressure falls below that certain number, right? So, but you got to make sure that your trials are independent, right? So each trial needs to be independent of the other trials. That's number one. Number two, there need to be only two possible outcomes of interest. The fact that there are only two possible outcomes is why we call this a binomial experiment. If there are three possible outcomes, or 4 or 10 possible outcomes, that would be considered a multinomial experiment. For us, we're only going to consider binomial experiments, so there will be two possibilities, success or failure. So notice before in the example that I gave, where I said you're going to give a pill, I didn't say you're going to see what is the blood pressure. No, I said you're going to test, is the blood pressure below a certain number? Because if you say, is the blood pressure below a certain ratio, I think this actually doesn't really make sense, because a blood pressure rating consists of two numbers. But, work with me here. You can say, did the person's blood pressure get to that level that we wanted it to? Yes or no. If it did, that's a success. If it didn't, that's a failure. Whereas if you structure your experiment and you say, hey, what was the blood pressure? That's no longer binomial, because there are too many possible outcomes, right? So for a binomial experiment, you should have only two possible outcomes, and we label them as success and failure. Okay. The third key component of a binomial experiment is that the probability of success is the same for each trial. And the last requirement is that we have a random variable, x, and x counts the number of successful trials. So remember, thank you. N is your number of trials altogether, right? And x is the number of successful trials. So that means that x could be 0, meaning you had all failures. X could be 1, meaning you had one failure, one success, and the other trials were failures. And any possible number up to n, right? So if x is equal to n, that means that every single trial had the outcome of a success. All right. So these are the symbols that we have. N is the number of times a trial is repeated. P, this little p, is the probability of success. So you'll notice here that we actually might, usually I'll use P and I'll use Q, as opposed to probability of success, P of S and P of F. So typically P and Q. And then again, we said with X, X could be any number, any integer, any whole number between 0 and n. A lot of times students forget 0 and n, but you have to include those, because it is possible that your experiment would have 0 successful trials, right? And your experiment could have 0 failures. All right. So these are the symbols N, P, Q, and X, and we're going to run through these. Always be looking for them when we're doing, when we're working the problems in the book and dealing with binomial experiments in general. Let's look at this first example. So pause it, read it. All right. So we've got a surgical procedure. The procedure has an 85% chance of success. And in chapter 3, or if you did that extra credit homework, that should reach out probably, because that should remind you of the fact that we have different types of probabilities, right? We have theoretical probabilities, where if you're rolling a die, what's the probability that you get an even number, right? And then we have experimental probabilities. So when this example says that a certain surgical procedure has an 85% chance of success, probably that's because they've done the experiment a bunch of times, right? In trials, because you know how you have to vet procedures before you perform them on humans, right? So, or you have a trial period, right? Because you can't just have a surgical procedure and it actually causes more damage to the patient. So in their testing, their experiments, before they get this surgical procedure and, start training all the doctors on it, they've gathered enough evidence and data to conclude that there's an 85% chance of success. Okay? So, a doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. All right, so now what do we have to check in order to check if this is a binomial experiment? First, we have to check if the trial, if the experiment is repeated for a fixed number of trials and the trials are independent, which we would say yes, trials are independent. Why? Because surgery on one person in the trial probably is not going to impact the success or failure of surgery on another person. Okay, so the trials are independent. What is a trial? A trial is, going back here, a trial is that doctor performing the procedure on one of those 8 patients. That's the trial. Okay, so that gets to, so number 2, only 2 possible outcomes for each trial. Yep, there are 2 possible outcomes. Success, the procedure was successful, or the procedure was not a success, right? The procedure was a failure. We can actually, while we're at it, we can write down how many trials? 8. And how do we know that? Because the doctor performs the procedure on 8 patients. So they were in trials. Each surgical procedure is a trial. Okay? So N is equal to 8. The probability of success is the same. Yes, we are given that P equals 0.85. Now, how did we get that? Right here, right? A certain surgical procedure has an 85% chance of success. That means P equals 0.85. So always when we're dealing with P, don't write 85%. It is instead expressed as a decimal. So when you're entering in percentages into your calculator, the convention is that you're putting in a decimal. So we convert that 85% to 0.85. Okay, and then X counts the number of successes. Yes, X does count the number of successes, and X is the random variable, right, representing the number of successful surgeries. So if 8 patients are, if the procedure is carried out on 8 patients, then X could be 0, 1, 2, any number up to 8. Okay, let's look at another example. So take a moment, read this, pause the video. All right, so we've got 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. All right, so here's our jar, and we could go, we've got 5 red, 1, 2, 3, 4, 5, 9 blue, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then some green, 6 green, 1, 2, 3, 4, 5, 6. So we've got these marbles, and imagine you shake the jar, right? And why am I saying you shake the jar? Because you randomly select 3 marbles from the jar without replacement. So you pick one. What is the trial in this case? A trial is selecting a marble. So your first time, you're going to pick a marble. It might be red, might be blue, it might be green. There you go. Now, without replacement, so now after the first trial, there are, well, how many there? Instead of being 20 marbles in the jar, now there are 19 marbles in the jar. Now, for the second trial, you're going to pick out another marble. Now there are 18 marbles. And then the third trial, you pick another marble. Now there are 17 marbles. And we are told here that the random variable represents the number of red marbles. Okay, so X is equal to the number of red marbles that you pick, right? Chosen from the bucket or whatever, from the jar. Okay, so already Let's look at this. Repeated for a fixed number of trials. The trials are fixed. So yes, the number of trials, for a fixed number of trials, yes. There are 3 trials, right? Because the 3 different times you're picking a marble. Are the trials independent? They are not independent. Why? Because the trial is to see if you pick a red marble, right? So now if I pick a red marble, that's going to impact my second trial because I'm going to start off from my first trial. What's the probability of picking a red? Would it be 5 out of 20? Because there are 20 marbles in there, 5 out of 20, right? So then I would have the probability of picking a red for the first one would be 5 out of 20. Now, when I go for my second trial, there are no longer 5 marbles, and there are 5 red marbles and 20 marbles altogether. There would only be 4 marbles, 4 red marbles and 19. So the fact that I picked a red marble is going to impact the probability of picking a red marble on my other trial. Do you see that? And even if I don't pick a red marble in my first one, I'm going to pick a blue or a green. That's still going to impact the probability that I pick a red one. It's going to make my probability of picking red increase, right? Because there are less non-red marbles in there. So no, right? No, it is not the case that the trials are independent. And at this point, we can stop and say that we do not have a binomial experiment. So just for kicks, we're going to go through and I want to show you that only 2 possible outcomes for each trial? That's true. Because each trial is picking a red marble, and when you pick each trial is picking a marble. When you pick a marble, either it's red or it's not, right? So success or failure. The probability of success is the same. This is false. As we said before, what happens in one trial is going to impact the probability of picking a red marble in the second, in the third trial. Okay, so the fact that this is not a binomial experiment is shown in 2 of the 4 requirements not being met. Okay, so now that we have a good look, and now that we're familiar with how to tell if an experiment is a binomial experiment, let's go ahead and get familiar with, I want to show you the binomial probability formula. And I want to show it to you to say that we are not going to use the binomial probability formula. So I'm not even going to call it out. I'm not going to explain what the notation is, because I really want us to use technology instead. If you are interested, then of course, a lovely exposition is provided in your textbook. Have fun, go at it. For the purposes of this course, I'm going to stick with just kind of focusing on using technology. Okay, the only thing new here is to introduce this concept of Q, which is 1 minus P. So Q is the probability of failure, right? So if P is the probability of success, then the probability of failure is going to be 1 minus P. Okay, so we're going to practice finding binomial probabilities. Now, what is a binomial probability? A binomial probability is essentially a probability that you have a certain number of successes in a binomial experiment. So let's look at this example. So knee surgery has a 75% chance of success on patients with degenerative knees. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Okay, so the first thing we want to do is verify that this is a binomial experiment. Now, when we verify it's a binomial experiment, what are we going to do? We need to know that we have a fixed number of trials. We do. How many trials do we have? 3. N equals 3. What is a trial? A trial is one patient having this microfracture knee surgery performed on the patient. Okay, either will be successful or it won't. What is the second thing we need to check for? We need to check for the fact that there are, also the trials are independent of each other. They are. If I operate on this person's knee, that's not going to impact the probability of success of the surgery on another person's knee. Okay, the second criterion that we check for is if there are only two possible outcomes of interest for each surgery. Yes, there are two possible outcomes, success and failure. Now, number 3, the probability of success is the same for each trial. Yes, what is that probability? It is going to be 0.75. And how do we get that? This is written in the problem. Okay, so we know that. And then 4, the random variable x counts the number of successful surgeries. So we've got that too. Now, what we're being asked to do is pretty specific. We're being asked to find the probability of the surgery being successful on exactly 2 patients. So what we want is, and this is the second thing, so after you've identified that your experiment is a binomial experiment, write down what you want to find. We want to find the probability that x equals 2. Because remember, x could be 0, 1, 2, or 3. X keeps track of how many successful surgeries there were. We want to find the probability that x is equal to exactly 2. Okay, so let's go ahead and let me rewrite my information over here. So we know that n is equal to 3. P is going to be equal to 0.75. And we want to find, our goal is to compute
1630.
Thank you. Our goal is to compute the probability that x is equal to 2. Here's how we do it. This is going to be on the calculator. On the calculator, you're going to click second distribution. Let me write it small over here. Now, I do have a video that explains all of this. There's a video on under TI-84 resources, which shows you how to hit those buttons and find it. For now, I'm going to just going to write down how to do it so that you can follow along. But feel free to pause, go back to watch the other video to show how to access Binomial PDF, and then come back and pick up here. Okay, so you want to go to second, and then you want to hit distribution. So if you have a TI-84, it might be a blue button. So you want second, and then because you ultimately want to hit distribution. And then from there, you're going to get a panel of a whole bunch of different choices. You want to choose the type of distribution. Because we're working with binomial probabilities, we want binomial probability distribution function. So you're going to go to, it should be A, binom PDF, right? And that's what that P stands for. So this is binomial. The P stands for probability distribution, and the F stands for function. Okay, so an up should pop a screen, and the screen will have something where it asks you for trials, it asks you for P, which is the probability of success, and then it asks you for X value, and then it'll say paste. Okay, so we already know that for trials, we want trials n equals 3. So for trials, you can put 3. For the P, which stands for the probability of success, is going to be 0.75. And then for X value, because we want to compute the value, the probability that X is equal to 2, you just plug in 2. Now, then you click paste, and what should show up, just to confirm, is binom PDF 3, 0.75, 2. and then you hit enter, and you should get the number. It should be I'm getting 0.421875. Okay, so in other words, there is a 42%, so about a 42% chance that exactly 2 of the surgeries are going to be successful. 2 of the 3. Okay. So the key thing I want to point out here is that we're using Binomial PDF. If you have a TI 83, you won't have this, right? You won't have this window pop up. What you'll have to do is you'll go to Binomial PDF, and then you will need to enter in this information right here. So you'll get something that says like Binomial PDF, comma, and then you have to, or parenthesis, open parenthesis, then you'll have to enter in 3, 0.75, 2, close parenthesis, enter. Okay. All right. So let's look at actually a binomial probability distribution. So notice that what I said here was you need to click distribution, and it is it'll give you a list of different distributions. Some distributions are really important and we're going to use them a lot. Normal distribution, binomial distribution, these are going to be the 2 key distributions that we use a lot. Okay, so let's look a little bit about look at binomial probability distributions. So in this example, what we want to do is list the possible values of x corresponding for the probability of each. Now, we're still in our same scenario as before. We already found out, let me try to make this a little bit heavier. Okay, so we already computed okay, so sorry about that break. So we already computed that the probabilities, so what are the options? What are the possibilities for x? X could be 0, x could be 1, x could be 2, and x could be 3. Remember, x is keeping track of your success, the number of successes. If you're doing 3 surgeries altogether, right, n equals 3, then x could be 0, 1, 2, or 3. And let me actually point this out. This is exactly the same table as we were doing in section 4.1. The only difference is instead of being up and down, it's going left and right. So instead of being vertical, we've just shifted our table to make it horizontal. We did this with our 4.1 lecture. Now, we just computed that the probability of x being exactly equal to 2 is 0.4218, right? Remember, we used our technology to compute that. So we can go ahead and put that in here, 0.4218. Right, 0.4218. Now we want to see what's the probability of having all 3 surgeries be successful. If the probability of one surgery being successful is 75%. Okay, so what are we going to do here? We're not going to use the binomial probability formula. We're going to use technology, and in particular, we're going to use Binomial PDF. So, let me see if I have a new page here. Okay, so for x equals 0, what are we going to put in here? We need to put in, you want Binomial PDF. N stays the same, so it'll be 3. Your probability of success stays the same, 0.75. But you want the probability that x equals 0, so you put in 0. That is, and then you hit enter, and that's what goes here. And then for Binomial PDF 3, 0.75, 1. That goes right here. and then binom PDF 3 0.75. 3 is what is the command that we would need to figure that out. All right. So let's see here. Okay. Sorry for that long gap. Let's move on to the next one. In the end, you'll have a table with the values, and what I want to focus on, I want to make sure that you understand how to, what commands you should be using. Because with the technology, once you figure out where everything is, then it's very simple to just, essentially you're just changing this value, right? So instead of 2, you're going to put in 0, click paste, then whatever spits out, that's what you put right here, right? And then you repeat that process. Let's look at this example right here. In a survey, U.S. adults were asked to give reasons why they liked texting on their cell phones. 7 adults who participated in the survey are randomly selected and asked whether they like texting because it's quicker than calling. Create a binomial probability distribution for the number of adults who respond yes. So first I want to verify that we have a binomial experiment. Now we need to have a fixed number of trials that are independent of each other. What are the fixed number of trials? What is a trial? Let's see here. It looks like our trial is explained right here. So there's 7 people that were given a survey, and they were asked whether they like texting because it's quicker than calling. The answer is either going to be yes or no. Yes, I like texting because it's quicker than calling, or no, that's not why I like texting. I like texting for a different reason, right? So n is equal to 7, and presumably these trials are independent because one person's reason for liking texting doesn't impact another person's reason for liking texting, okay? The second thing we would need to verify is that there are only 2 possible outcomes of interest, and again, yes, that's true. Either yes, that is the reason why you like texting, or no, that's not the reason why you like texting. The third thing is that the probability of success is the same for each trial. What is the probability of success? I don't see a number here. That's where we need to scroll down and look here. So why do we like texting? Here we go. Quicker than calling. 56% of people said because it is quicker than calling. So that is our P. Our P is going to be 0.56. Because what's the probability that you like texting because it's quicker than calling? 56%. Okay, so now let's see here. We want to create a binomial probability distribution for the number of adults who respond yes. And we're going to use technology to do this. Okay, so in our technology, so we'll have X. So we've got X and P of X essentially, right? And now we need to calculate, because what are the values for X? I should have written this down here. X can be 0, 1, 2, any number up to 7, right? So X can be any number from 0 up to 7. We are at stage 2, which is using technology. Okay, so our probability distribution, we can write it on its side. We don't have to write it up and down. So we have X, and here's going to be P of X. Now, we need to know here, what's the probability that X equals 0? Okay, how do we get this? We're going to use binom PDF. We need to put in P and then our X value, right? So we would have binom PDF. N is 7, P is 0.56, and the X value we're looking for is 0. And then you get a number, and you write that right there. And then we'll have for 1, 2, 3, 4, 5, 6, and all the way to 7. right? And each time you just change this last little x value, right? So this number here should match your x in the top. So for example, if we want to know what number goes here, what's the probability that all 7 people will say, yes, I like it because it's quicker? We would say probability x equals 7 is going to be, we need binomial PDF 7, 0.56, and our x value is 7. And that's going to spit out some number, and that is the number that you put in that little box. Now, when you do this, these are the answers that you should get, and these are rounded. Notice that all of the probabilities are between 0 and 1, right, which is what we expected. That's what we talked about in section 4.1. All of the probabilities are between 0 and 1. And if we add up the probabilities, it is close to 1, right? So if you add these up, I think you get 1.000001. The reason why it is close to 1 and not exactly 1 is because of rounding, right? So for instance, we rounded a little bit for this value here. You actually, on your calculator, will get 0.00319277881, right? And it's even, dot, dot, dot. So when you're rounding, then you introduce error. Okay, now we're finally getting to an example. Here's another example where we're going to use binomial probabilities. We're going to use technology to find binomial probabilities. I'm going to give you a moment to verify that this is a binomial distribution. Sorry, binomial experiment. And at the result of that, you should be able to tell me N. You should tell me P.
445.
It's 1645.
Thank you. And the possible values for X. All right. So our P is going to be 0.67. N is equal to 100. And so X could be 0, 1, 2, anything up to 100. For the question that we're asked what is the probability that exactly 75 adults consider it an air conditioning a necessity? So we want to, number 2 is set up, we want to find what is the probability that X equals 75. And now we already know that the command that we need to use is binomial PDF. We need to put in N, we need to put in P, and then we need to put in the particular X value that we're looking for, which would be 75. Let's see, make sure that you can see that. So this is what you should be looking for on your calculator. Okay, so this is what you should have on your calculator. And in this next slide here, this is what yours should look like. So we could round this up to what percentage? What is the probability that exactly 75% of the adults consider air conditioning a necessity? About 2%, right? Because 0.0201, move that over 2, and we get about 2.01%. So very few adults, right? What's the probability that exactly 75 adults consider air conditioning a necessity in that trial? It's a very small probability that exactly 75, right? Okay, so we're not going to use formulas. We are going to use technology again. So I want to say number 1, pause, read the question. All right, so now first step is to verify that we have a binomial experiment. And we do. So you should be verifying out loud, making sure you understand how to verify. We've done that several times now, so I'm not going through it explicitly. And the result, we should be able to tell N, P, and options for X. So N is going to be 4. How did we get that? Because what is a trial? A trial is asking a U.S. woman, right, 4 U.S. women, asking a U.S. woman if reading is your favorite leisure time activity. And the person is going to either say yes, it is, or no, it is not. What is the probability that this U.S. woman is going to say yes? 41%. How do we get that? That's written in the problem here. Indicates that 41% of women in the U.S. consider reading their favorite leisure time activity. And now X is keeping track of the number of women in the trial that say yes, it is my favorite leisure time activity. So 0 women could say yes, 1, 2, 3, or 4. Now, the second thing we want to do is set up and write the probability. So what is the probability that we need to investigate? We're trying to see what is the probability that at least 2 of them respond yes. So we want to know what's the probability that X is at least 2. X is greater than or equal to 2. That's what we want. Okay? So now what I wanted to do is I wanted to first kind of draw this probability, make a probability table. So just to kind of show what we're doing here, now we know how to find what's the probability that 0 women say, yes, it's my favorite. That would be to use Binomial PDF. And then we need N, which will be 4. We need P, which is 0.41. And then our X value would be 0. And that should give us about 0.127174. Right, and then we can continue this for what's the probability that one woman says yes, and the other 3 say, nope, it's not my favorite. Paste. So to have it here, and then paste. I can go ahead and paste because it's the only thing that I need to change as I create my table is the X value, which is that last little position, right? So I can go ahead and just, this is going to be 1, 2, 3, 4. And then what are the probabilities that I get? So I get 0.3368, 0.35109, 0.16265, and 0.02825. So if, for example, if the probability that women consider reading as their favorite leisure activity is 41%, then, so if 41% of women consider reading as their, number one leisure activity, then the probability of all 4 people that you survey saying, yes, it is my favorite is like 2.8%, right? Because the question is, if 41% of women consider it their favorite and you survey 4, you would expect about, maybe a little bit less than half, maybe 2 women to say, yes, it is my favorite leisure time activity. So it'd be very unlikely that all 4, that you're going to find 4 women that say, yes, it's my favorite activity, if the probability that it's your favorite is only 41%. Okay, now let's get to graphing this, because I want to show you, now this is, so the probability for 0 is going to be about 12.74. So I'm just estimating something a little bit over, right? I am just estimating something that is a little bit over. So this is 0.127, a little bit over halfway up. And then for the 30, the probability that X equals 1 is like 30. Okay, the probability X equals 2 is a little higher, 35. I know it's not accurate, but it's okay. And then we drop down to 16. And then the last one is like 2%, which is, I don't even know if that's, okay. This is like 0.34, 0.35, 0.16, and 0.0. I just rounded up to 3. Okay, Now, the question that we need to investigate is, what is the probability that at least 2 women? So at least 2 women means 2 or 3 or 4, right? That's what we want to find, is at least 2 women. What's the probability? So one thing we could do is we could just add up these probabilities. That's one thing we could do, is add up these numbers, which is the same as adding up this area here. However, there is a function on the calculator which will do it for us. And I want to introduce you to that function. It is binomial CDF. Now here, the C stands for cumulative. Let's see here, let's make it. Binomial stands for binomial. The C stands for cumulative. The D stands for distribution. And the F stands for function. Okay, so now what does the binomial CDF do? It has the same input, except binomial CDF keeps track of the probability of less than or equal to X successes. So for instance, if I were to put into my calculator binomial CDF, and then I put in N is equal to 4, P is equal to 0.41, and my X value is 2, this would give me not what I want. It would give me the probability of having 2 or less, right? Which is 2 or less successes, which would be the same as adding the probability of 0 successes plus 1 success plus 2 successes. What we want is we want the probability that X is greater than or equal to 2, right? So we want probability that X is greater than or equal to 2. So what we need to do is we need to rewrite this in a way so that binomial CDF can actually give us what we need. Okay, because binomial CDF will only tell you the cumulative probabilities, and cumulative probabilities mean you're working with less than or equal to. Okay, remember when we had our frequency distributions, right? You would have your frequencies, and then you would have your cumulative frequency, and the cumulative frequency adds everything above it, remember, which is the same as everything less than. So it takes those F values, the frequencies, and it adds all of the frequencies at that stage or less, right? All of the frequencies of that class or less. So what we need is we kind of need the frequencies bigger than the class. So we've got to play around a little bit, and that's what I want to show you now. We've got to play around with the probability. So we want the probability that X is greater than or equal to 2, which is kind of like here's 2, and then here's 3, and then 4. Okay, so we want greater than or equal to 2. We know that cumulative binomial CDF only keeps track of things less than or equal to. So we're going to say that we know that probability that X is greater than or equal to 2 is the same as 1 minus the probability that X is less than or equal to 1. So let's look at this. So less than or equal to 1 is going to be over here, right? So that is the probability, because if here's 1 and then here's 0, the probability that you're less than or equal to 1 is going to be to the left. And we know that when we add up all of the probabilities, it has to equal 1, right? So if we want the probability that X is greater than or equal to 2, we rewrite it like this. And then we can use binomial CDF. We put in our P, which is going to be, our N is 4, P is 0.41, and now we put in 1. And this is how we get the correct answer. So this should be approximately 0.542. Okay, and I want to introduce this to you because this is going to be this skill of being able to look at our distribution, a graph of the distribution, and play around with are we going to the left? Are we looking at the terms to the right? 1 minus, all this stuff is going to really come into play for the rest of the semester. So that's why I want to introduce it to you earlier. So you can do it just by adding. You can do this problem just by adding up each of these probabilities. However, sometimes there are a lot of probabilities to add up. And it's faster to use your binomial CDF. Right, so remember your binomial CDF. CDF is when you want cumulative numbers. PDF is when you want exact numbers, right? So if you look at this, you'll see here they're being explicit, exactly 75, which is different from at least 75 or less than 75. Okay? All right. So let's look at this one, this example. And again, we're not going to be using a table. We're going to be using technology. About 10% of workers in the U.S. commute to their jobs by carpooling. You randomly select 8 workers. What is the probability that exactly 4 of them carpool to work? Okay, so the first thing we're going to do is verify that we have a binomial experiment. Go ahead and do that.
It's 5 o'clock.
It's 17 hours.
Okay, go ahead and do that. And now, let's go ahead and you should see that N is equal to 8, P is equal to 10%, right? Because it gives us the information that about 10% of workers, right? So 10% is the probability of success. What is a trial? A trial is asking one of those 8 workers, do you commute by carpooling? And they'll say yes or no. What we want to find the probability that exactly 4 use carpool. So what we want is the probability that x equals 4. How do we do it? Binomial PDF. You put in N, which is 8. You put in P, which is P equals 0.1. And then you put in your x value, which is 4. And when you do that, you should get, not 4. This is incorrect. The x value should be, no, that is correct. That's correct. Sorry. The x value should be, 4, and this should give you approximately 0.005. Okay, now, yeah, so that's all we need is binomial. We've got the syntax here. Binomial PDF, N is 8, P is 0.1, X is equal to 4. Okay, and now, graphing a binomial distribution. 60% of households in the U.S. own a video game console. So already, as we're actively reading, 60% of households own a game console. That's telling me that my P is 0.6. What's the probability that you own a video game console if you're in the United States? Apparently it's 0.6 or 60%. You randomly select 6 households. So N is equal to 6. And the trial is asking that household, do you own a video game console, yes or no? Okay, we want to construct a probability distribution for the random variable x, then graph the distribution. So x could be 0, 1, 2, all the way up to 6, right? And when we do our probability distribution, essentially what we're going to plug in, because x could be 0, 1, 2, 3, 4, 5, or 6. For here, we need the binom PDF. What is n? N is 6, p is 0.6. So 6, 0.6, and then our x value of 0. And that'll give us approximately 0.004. And then approximately 0.037, 0.138, 0.276, 0.311, 0.187, and then the last one, 0.047. And we already did an example where we graphed the distribution, but here's, so you can look in here and see that what you do is you just, your midpoint is the probability, right? The x value, 0, 1, 2, 3, all the way up to 6. And then you just draw the bars up as how tall are the bars. It corresponds to the p of x. So your vertical axis is probability, and your horizontal axis is the number of households that have video consoles. All right, so we're getting towards the end here. This is the last concept that I want to introduce you to, is finding the mean, variance, and standard deviation of a binomial distribution. I wanted to put that in there because we know how to find, we have these complicated formulas for the mean, the variance, and the standard deviation of a distribution in general, right? So we had something like the sum of x times f over the sum of f as the formula for the mean of just a regular distribution. Because and this was used to estimate, right? Remember that the best we could do is estimate. If we had a class, the best we could do is estimate, and the x here is using the midpoint of each class. Now we can actually compute the mean, the variance, and the standard deviation if we know that we have a binomial distribution by using these formulas right here. Okay? So, in your preparation for the next exam, you should be making notes, put a star by these formulas, have these formulas, write them on a separate sheet because they're easy to forget, but they're really, they're really helpful and they really save time. So you want to just make sure that you know that you don't forget these formulas here. Okay, so let's look at this example here. In Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. Okay, so we want to verify that we have a binomial distribution. We do. What is a trial? A trial is looking outside on this day in June, June 2018. On each day, you look outside and you say, is this a cloudy day? Yes or no? Right? June 1st, is this a cloudy day? Yes, it is. June 2nd, is this a cloudy day? No, it's not. June 3rd, is this a cloudy day? Yes, it is. Right? So what is N? N is going to be the number of days in June because each day in June is a trial. How many days are in June? 30. Now, what is the probability of success? What's the probability that a particular day in June is cloudy? Was given to us in this problem. 56% of the days in a year are cloudy. So P is going to be 0.56. And we will need, because our formulas involve N, P, and Q, right? We will need Q. What is Q? Is, if you recall, Q is the probability of failure. Q is 1 minus P. So let me put that here. Q is 1 minus P. It's the probability of failure. So if the probability of success is 56%, the probability of failure is going to be 1 minus 56, or 1 minus 0.56, which is going to be 0.44. Okay. Now we can apply the formulas, right? So find the mean, variance, and standard deviation. Well, for the mean, mu, is just n times p, which is going to be 30 times 0.56, which is going to be 16.8. What does that mean? So we're actually jumping to this part about interpret the results, right? What does it mean? Ha ha ha, mean. What does it mean to say that the mean is 16.8? Here's what it means. If 56% of the days in a year are cloudy in Pittsburgh, then on average, you can expect about 17 days in June to be cloudy. So this is similar to that expectation. Expect about 17 days in June to be cloudy, which is what you would kind of expect. If about 50%, right, there's 50% of the days in the year are cloudy, then you'd expect 50% of the days in June to be cloudy. What's 50% of the days in June? 0.56 times 30, 16.8. Okay? And we can do the same thing with variance. So with variance, we'll have sigma squared is n times p times q, which will be 30 times 0.56 times 0.44, which is going to be about 7.4. And we have our standard deviation. So let me go somewhere else. So just to recap, our mean is 16.8. Our variance is about 7.4. And our standard deviation, remember that's the square root of variance, right, which is going to be the square root of NPQ, which is going to be the square root of really 7.4, right? So it's going to be approximately 2.7. Now, the last thing that we're going to do is to interpret the results and determine any unusual values. Okay, so what I have here is a graph of the distribution. This is a graph of the distribution of cloudy days in June, right? Based on the fact that we've got 30 days in June and 56% of the days in a year are cloudy in Pittsburgh. This is all in Pittsburgh. So for instance, what's the probability that you're going to have no cloudy days? It's so small that it doesn't even show up, right? It's less than 4%. It's very, very small probability. The only time that when does there actually become a probability that's noticeable is 9, right? 9 cloudy days. And then on the other hand, what's the likelihood or what's the probability that all 30 days are going to be cloudy? Very unlikely. Why? Because typically, right, 56 days or 56% of the days are cloudy in Pittsburgh. So what's the likelihood that you're going to have 30 cloudy days in a row? So small it's close to 0. Okay. So on average, and we've got down here, you can see the mean right here and the standard deviation and the variance. And that 16.8 is, if you notice, we're working with something that's symmetric. That 16.8 is, this is 15, 9, 10, 11, 12, 13, 14, 15, 16, 17. So it's somewhere like here. Notice again that the mean is not an actual value. You can't have exactly 16 days cloudy, because we said there's day 1, day 2, day 3, right? There are only 30 days. How can you have 16.8 days? The mean does not have to be an actual value point, right? The mean is an estimation. It's the same as when you just have a data set, right? A whole bunch of numbers and you find the mean. That mean might not actually be in your data set. Okay, so that was a problem on the exam. It's a key concept for you to recognize. Now let's talk about which values are considered unusual. Clearly, it would be unusual to have 30 days of, clearly it'd be unusual to have 30 cloudy days, right? Why? Because that is so far from the mean. So let me put that mean back in there. The mean is here, right? So that's our mu. The mean is here. The mean is equal to 16.8. 30 is so far away from 16.8. Here's how we tell the rule of thumb for unusual. Rule of thumb. So more than 2 standard deviations away from the mean, that's what we mean by unusual. An unusual event. So for us, we've got to figure out what's more than 2 standard deviations away from the mean. So we can go 2 standard deviations above the mean. Now, what is our standard deviation? Our standard deviation is 2.7. So we can go 2 standard deviations above, which would be 16.8 plus 2 times 2.7, right, which would give us 22.2. 21, 22. It looks like 22.2. So this right here is mu plus 2 sigma. Mu plus 2 sigma. And now we could go 2 standard deviations below.
It's 17:15.
Which is going to be 11.4. So 11.4. So that is mu minus 2 standard deviations. So let me go over here and write this down. So mu plus 2 standard deviations would be 16.8, right, because there's mu. And now our standard deviation is 2.7 plus 2 times 2.7, which is about 11.4. Sorry, which is about 22.2. And then we have mu minus 2 standard deviations, which is 16.8 minus 2 times 2.7, and this is 11.4. So what we're saying is that if there's a month, if there's a June, if there's a year in which, let me get my right color here, in which you have more than 22.2, more than 22 days of more than 22 cloudy days, or less than 11 cloudy days, that is unusual. Okay, so that is how we interpret it. So more than 22 cloudy days, or less than 11 cloudy days is unusual for Pittsburgh. And how do we find that? Again, we looked at which days are more than 2 standard deviations away from the mean, right? So you could be 2 standard deviations above the mean or more than 2 standard deviations below the mean. All right. So one of the homework questions, the written homework question, requires you to draw a picture of the graph. And you don't need, because the graph actually has like, I don't know, the n for that problem is very large. It's very, very large. And you don't need to, you can just do a sketch, right? You don't need to sit and try to draw like 1,000 different bars. But I will post the link to the applet. So there's an applet. This is an applet from University of Iowa. and it allows you, so I just put in my N, I put in my P, and then it automatically graphs the binomial distribution for you. So I'll post that and you can play around with it. Thanks, that's it.